Okay, so let's start our look at gears. So we got different types. We got spur gears, bevel gears, straight teeth. You can have helical gears. You can have helical gears with sorry, you can have bevel gears with helical teeth as well. Got worm gears, rack and pinion drives, ring and pinion drives. So essentially, they're all different methods of transferring rotational power or linear motion to to some other form of rotational power and or linear motion. So obviously the rack and pinion drives are working off linear motion on the rack portion, but via the use of intermeshing teeth. So they're quite efficient. So we're efficient and durable compared to other methods of kind of transferring power like this, especially one of the main things you're using gears for is to transfer the power from a higher speed, lower torque situation to a lower speed, higher torque. Um, so that'll the same total amount of power is maintained, other than the bit of efficiency loss that we get here, than that other 2% or so. But we're able to kind of take our inputs and put them into something that's a bit more useful. So the American Gear Manufacturing Association is the one that's primarily in the lead of kind of developing standards for those. And yeah, we want to be producing torque that providing the we needed to basically be able to transform our torque levels and our rotational speeds as needed through the use of meshing rolling surfaces. So involute profiles were discovered to be kind of the most optimized way to transmit that rotation. So an involute profile is this basically kind of shows how you start off with an involute profile. If kind of if you tie a string to a pencil and kind of just lead it off like that, that'll cause you to have an involute profile. So where like the distance from as you move the pencil up this way, it kind of you know the it moves up, but the string gets a bit longer as it kind of uncoils. So here's kind of another example of the generation of an involute from the base circle. So we're starting off from this base circle here, and that's kind of like the start of the kind of the diameter where the you're starting to unspool from, and that leads to gear teeth that will have kind of this involute profile on their meshing on the surfaces that they're meshing with the other teeth. When we talk terminology, the pinion is going to be the member that has less teeth, and the gear will be the one that has the more teeth. So if we're trying to go from a high speed, low torque situation down to a high torque, lower speed, the pinion will be the one driving it. We also sometimes have setups where all you're trying to do is kind of offset the rotation, but keeping the same. If you want to keep the same direction of rotation, then what you're going to need to do is you're going to need to have what we call an idler gear. So you can have a driver gear, and that'll uh, and an idler gear in the middle and a driven gear. So basically the driver gear will cause the idler gear to have a certain amount of rotation, then that idler gear will cause the driven gear to have a certain amount of rotation. So the rotational speed of the idler gear here will be faster than either of these two. It'll because when we go from the driver gear to the idler gear, we got more teeth here. So for each rotation of the driver gear, the idler gear needs to rotate a bit more. But then when it gets back to the driven gear, each rotation of the idler gear causes a fraction of a rotation of the driven gear. So the net effect here would be to essentially just offset the axis of rotation between the driver gear and the driven gear. That's because the driver gear and the driven gear have the same number of teeth. You can also have setups where you have a different number of teeth for the driver gear and the driven gear, while still having an idler gear in the middle. So then you're going to still affect some change in the torque and some change in the rotational speed, but the idler gear in the middle ensures that both the driver gear and the driven gear are going to be rotating in the same direction. So uh, some nomenclature. So got the topland up at the top. Got the addendum circle. That's basically the circle that kind of outlines the very end of the teeth. You've got the addendum circle. That's going from the very bottom of the teeth. And then you've got the pitch circle. So the pitch circle is basically kind of like the circle that defines the diameter at which the teeth come into contact. You've got the let me think here. Yeah, so each of at the kind of corner of the teeth, you're going to have a little fillet radius here. So it's, oh, didn't mean to click there. And a fillet radius here, so that the size of that radius is going to kind of affect your stress concentration going on. The face width is obviously also going to be like the width of the gear itself. The tooth thickness is based upon the thickness of the tooth at the pitch circle. We've got this clearance here at the bottom here. So you notice that that's basically kind of the gap between where we have the start of the involute profile and the very bottom, because the involute, this line here, that's the involute profile, and then we are able to, and then it kind of, obviously it stops being an involute and moves on over to the other tooth. So this little gap here is the clearance. And basically, for meshing, basically what you don't want is any of the other teeth that are going to be coming into contact here. They shouldn't come into contact any further. They should never come into contact any further down than the start of the involute profile. So we got the tooth thickness. We got the slot width as well. Yeah, so the pitch, the diameter of the pitch circle is going to be quite important, and then the circular pitch, that's the distance from one tooth to the next tooth when measured, kind of from points on the pitch circle. So essentially, when we're modeling these, how these work. Kind of, we model them as if like if we just had two cylinders here that were rotating and all the energy was transferred via friction, then the line of action would be basically at the same portion of the pitch circle. So this gear here is equivalent to this gear here, this circle here, in terms of rotational speeds and so on and so forth, and that's measured at the pitch circle. So like I said, the pitch circles is where we basically kind of get the it's where the teeth are going to be in contact when the point of contact is directly between the two center lines. So it's not necessarily where they're in contact, like in this situation where it's meshing, up here. But when these rotate a bit further and the point of contact is right in the center here, then that's where then it's going to be at the intersection of those pitch circles. And then the center distance is based upon a kind of a combination of the based upon the offset between the two. So one thing that is good about gear teeth with an involute profile is that when they do come into contact, the teeth, as they come into contact, kind of come into contact and they mesh so that the contact between the two teeth causes a normal force at a constant angle. So that's what we call the pressure angle. So there's a line of action, kind of from where they come into first contact until when they leave contact, and that line of action kind of moves along here, and that entire time the teeth are normal to one another and they're causing pressure at the same angle. So you can kind of see that in action here. So you get the point of contact just moving along as the teeth come in and out of contact with one another. Okay, gotta remember I need to keep moving my mouse for you guys to see the GIFs going on. But yeah, it's the point of contact moves along at a particular angle and the pressure moves on it at a particular angle. So the force imparted from one gear to the other is always going to be at that angle. So and here's just this next one's just kind of an example of how these get generated. So kind of one way that we can form gear teeth is by taking like a rack and kind of rotating, using it to cut the gear tooth as it moves around. So I'm just gonna exit out of this and kind of replay that, because there we go. So you can kind of see how we started out. With kind of a straight rack and just rotated it around to cut out a gear tooth. So this is kind of the geometry of a gear that you might use. A gear. A rack cutter that would be used to cut that. So basically, this pitch here up top that corresponds to the same pitch that you would end up with for your what am I trying to say? For the gear, and the angle alpha here is going to be your pressure angle as well. So yeah, our line of action, got a pressure angle acting along that line of action. So when we're talking pitch, so there's kind of the two different types when we're talking imperial or conventional units. I really hate that term, just because, yeah, they should not be viewed as conventional. But anyways, so we got circular pitch. So that is pi times the diameter divided by the number of teeth. And that'll be a measurement that is in inches. And then we got our diametrical pitch. That one's a bit more common, and that's basically kind of to a degree. It's the number of teeth divided by the diameter. So that'll give you a value in per inch. That tends to be more commonly used. So the difference between if we're going to be using large P for the diametrical pitch and small p for the circular pitch. And then metric tends to use the gear module or gear modulus. That's a measurement in millimeters, and that is just the diameter divided by the number of teeth. So similar to the circular pitch, so they don't bother using pi. And then if we wanted to kind of convert one to the other, what we can do is we can take the diametrical pitch, the big P, take 25.4 and divide it by that, and that'll give us our gear module in millimeters. So the gear ratio is also fairly important. So that's a function of the gears that we are using to mesh together and kind of how they will rotate. So if we have the rotational speed of the pinion divided by the rotational speed of the gear, that will be equal to minus, because it's switches rotate, it switches direction, so we throw the minus on there, minus the diameter of the gear and divided by the diameter of the pinion. Now, of course, since the pitches are since if we want these gear teeth to mesh together, they need to have the same pitch, then we can also relate that in terms of just the number of teeth. So knowing that this P here is a constant, therefore these values here, the number of teeth in the pinion divided by the diameter of the pinion needs to be equal to the number of teeth in the gear divided by the diameter of the gear. We can also relate the gear ratio in terms of just the number of teeth. So the rotational speed of the pinion divided by the rotational speed of the gear is just going to be equal to minus the number of teeth in the gear, excuse me, divided by the number of teeth in the pinion. So yeah, in this instance up here, our gear ratio, oftentimes you do drop the negative, but or when we're talking gear ratio, we usually just actually talk about kind of the ratio between the teeth. So this would be a 3-to-1 or gear ratio, since we got 8 teeth here and 24 teeth here. So some typical values for kind of diametrical pitch, a quart, ones that would be kind of considered coarse would be kind of in the half-inch to 10-inch, half per inch range to the 10 per inch range. Medium coarse, 12 to 18. Fine, 20 to 128, and then ultra fine, 150 to 200. So here's kind of looking at how those might look. So up here in 2, we're looking at These would all be considered coarse, and then we're looking more at medium coarse, and then fine gets even kind of smaller than that. And here's just another kind of a chart that kind of shows how they might look kind of on actual on gears of this size. So obviously the 4 fairly chunky teeth, and then we get down to I think the 80 is the smallest here. So yeah. So as your pitch gets as your pitch gets larger, your teeth get smaller, both in terms of the gap, and obviously if the gap between the teeth, and if the gap between the teeth is getting smaller, then obviously the actual length of the teeth has to get smaller too. Available sizes in metric, you can usually get them around 0.2 to 5 millimeter in terms of your gear module in certain increments. So these are the increments you can usually find them in. So you can get 0.2, 0.3, 0.4, up to 0.1, and then 0.1, 0.1, 1, 1.25, 1.5, up to 4, and then 4.5, 4.5, and 5. Obviously, the pressure angles also need to be matching for these gears to work together properly. So typical standard pressure angle is going to be 20 degrees. 25 is it. Oh, yeah. 25 comes up sometimes, but not as common as 20, and 14.5, it's less used nowadays. You might still find it, especially more so on some legacy systems that you might be working with, but you're probably not going to be using it for current designs. So there's standard sizes available for the length of the teeth as well. So if we are talking pitches that are less than 20, so the coarser gears, and again at a pressure angle of 20 degrees, then for either of them, the current standard for either pitches below 20 or pitches above 20, the current standard is for an addendum to be equal to 1 divided by the pitch. That is sometimes going to result in a tooth that is a bit too long to be able to mesh properly with the other gear. So they used to use what we call a stub gear. You can still find them. They're not part of the standard nowadays, but you can still find them for replacements, and some people still use them for current designs. Probably not recommended, but those will basically shorten the addendum by 20%. And then the addendum will be for coarse gears. It'll be 0.125 times the addendum. 0.125 times divided by p. So 25% larger than the addendum for standard gears, even more, a fair bit larger than the addendum for stub gears. And then when we get to finer gears, basically 20% more than the addendum, plus a little, plus 2 thou. The face width also comes in kind of a standard range of available sizes, 8 over p to 14 over p. Basically the wider the gear is, then basically kind of the harder it is to mount properly. So basically, the wider it is, the more critical the the angle you're mounting it at needs to be. And we got our curvature radius at the at the root. So that's it right there. Relatively standardized for coarse gears, more variable for when we get to our smaller gears, our finer gears. And we're worried about this because we're worried about interference. So basically, like I mentioned before, when your teeth are meshing together, you want to make sure that the tooth isn't sticking out far enough that it will kind of touch any of the non-involute portions of the opposing gear tooth. So you want to have a maximum radius of the addendum, and that is based upon the base circle of the gear you're looking at, plus the center line distance between the two gears, times the sine squared of the pressure angle. So that'll basically kind of give you the largest distance from the center of the gear out to where the addendum needs to end. So if your actual addendum, which again is your diameter divided by 2 plus your actual radius of the addendum, which is your diameter divided by 2 plus your addendum, is less than that, then you should be good. Another way of looking at this is basically this ends up causing problems essentially when you have a certain number of gear teeth. So when you have a low number of gear teeth on the pinion, then it is most likely to cause interference. So this formula here gives you a minimum number of gear teeth on the pinion that you can use in order to avoid interference. So this K value here, it's going to, for full gear teeth, 1.8 for stub teeth. And then the other values are again, our pressure angle, our gear ratio, and yeah, that's it. So yeah, as long as you're using a sufficiently large number of teeth on your pinion, and again, remember the pinion's the one with the fewest teeth meshing together, then we can avoid interference. We've also got the contact ratio. So again, when we have the gears meshing, the gears rotating, you're gonna get you're gonna have contact between the gears, between at least one set of gear teeth at all times. But you'll see that at some portions during this process, you've got two gear teeth in contact. So your contact ratio is basically determining how much of the time do we have both those gear teeth in contact. So that'll be based upon the geometry that we're looking at. So again, the radius of the addendum for the pinion, the radius of the base circle for the pinion, the radius of the addendum for the gear, the radius of the base circle for the gear. So those two parameters are basically kind of the radius at which contact might start and the radius at which contact would end. So the base circle is the start of the involute profile. The addendum is the radius of where the end of the tooth, and then the center line distance between the two and this angle, the pressure angle, and then all that divided by and then our diameter of the base circle. So the diameter of the base circle for one of the gears divided by the number of gears of the teeth. So again, those radius, this will be for one of the gears, and it'll correspond to the number of gears, number of teeth in the gear. So either the gear or the pinion. This ratio here is going to be constant for both the gear and the pinion. Now that's for the base circle there. And again, the base circle is can be found the the ratio between base circle divided by the diameter of the gear, and again that's the pitch diameter of the gear. So like the point that's right between the didendum and the addendum, that is cos of the pressure angle. So we can take that value there, plug it into here. So then we'll have we'll have pi cos phi d over n. So again, our d over n, or since we're plugging that in, p is equal to n over d. So we can plug in our p value for this value here. So then we're left with everything as a function of the various base circles and addendums, and the pressure angle and the pitch. So when we have a high contact ratio, it's going to be smoother, less noisy when it's meshing. So we generally want something, in the 0.12 to 0.16 range. So yeah, if we're always going to have one pair of gear teeth engaged at a time, unless it's the worst gear solution ever. And then some of the time, so 20, like in this case, 20% of the time we're going to have the two teeth in contact if we have a contact ratio of 1.2. So let's go through an example. Okay, so we got an electrical motor supplying the input here. And got the output coming out here. These shafts are parallel to one another, and we got a center line distance of 6 inches. C is equal to 6 inches. One stage, so we're only using one pair of gears, and we want a transmission ratio of 3 to 1. Gear ratio 3 to 1. And they specify here that we're looking for a diametrical pitch of 6. P is equal to 6. Keep in mind that the units for that are inches to the -1, or 6 per inch. And we're looking for a pressure angle of 20 degrees because that's what's primarily commonly available nowadays. So we want to size both elements. So we know that we're mounting them 6 inches apart. So we note that the radius, we're mounting them 6 inches apart, and we're ideally going to be mounting them such that the pitch circles for each of them touch. So we want the radius of the pinion plus the radius of the gear is equal to 6 inches. Or if we want to work in diameter, the diameter of the pinion plus the diameter of the gear. That's going to be equal to 12 inches. So we also know that the gear ratio needs to be 3. So the number of teeth on the gear needs to be 3 times that of the number of teeth on the pinion. The diameter of the gear needs to be 3 times that of the diameter of the pinion. So we have diameter of the pinion plus 3 times the diameter of the pinion. Subbing that in, that needs to be equal to 12 inches. So therefore we can solve our diameter of the pinion as equal to 12 over 4 inches, 3 inches. So in terms of radius, our radius of the pinion is equal to 1.5 inches, and the radius of the gear is equal to 3 times that, 4.5 inches. Adding those two things together gives us 6 inches. So diameter of the pinion is 3 inches, diameter of the gear 9 inches. So we got the sizing. So our pitch diameters is going to be the 3 and the 9. So number of teeth. So there we're working with our diametrical pitch of 6. So again, just going back to our little definition right here of diametrical pitch. Diametrical pitch is number of teeth divided by the diameter. So P is equal to N over D. So 6 per inch is equal to, let's go for the pinion first. 6 per inch is equal to 3. Oh wait, is equal to N divided by 3 inches. So solving for the number of teeth of the pinion, that's going to be, I guess I need to, number of teeth of the pinion is equal to 6 per inch times 3 inches. And inch is equal to 18 teeth. And then for the number of teeth of the gear, we know that that is going to be 3 times that. So that'll be 54 teeth. So checking for interference. Let's go back to this equation here. So the minimum number of teeth of our pinion needs to be, I'm just going to copy that. Oh, maybe not. I'm going to screenshot that. So the minimum number of teeth of our pinion to avoid interference is going to be equal to 2 times k. K, we're talking full-size teeth here. So k is going to be 1. So 2 over 1 plus 2 times, our gear ratio is 3, times sine of 20 degrees squared times our gear ratio of 3 plus the square root of our gear ratio of 3 squared. So 9 plus 1 plus 2 times gear ratio 6 times the sine of 20 degrees squared. So let's see here. Sine of 20 squared that is equal to 0.117. Looks more like a 2. Should be 7. So 2 over 1 plus 6. That's 2 over 7 times 0.117 times 3 plus the square root of 9 times 7 times 0.117. 0.117 times 7 is 0.819. So 2 over 0.819 times 3 plus the square root of 9 plus 0.819. So 0.819 plus 9. Take the square root of that. That gives us 3 plus 3.13, 6.13. To add those two things together, 2 times 6.13 divided by 0.819. That gives us an NP min is equal to 14.9. Obviously, round up to the next largest number because we can't have a non-integer number of teeth. So 15 teeth. So the minimum number of teeth that we want is 15. We have 18. So we are successfully avoiding interference in that case. So checking that, and then the contact ratio. So our contact ratio again, screenshot this and drag it on down. Okay, so we are going to look at the radius of the pinion. We need, the addendum radius of the pinion and the addendum radius of the gear. So the addendums for each of these should be the same because they're the same pitch. So if we're going for the size of the addendum, then we should be working with 1 over p. So the size of the addendum should be equal to 1.0 divided by 6 per inch. And that'll give us 0.166 repeating inches. So the radius of the addendum for the pinion is equal to 0.166 repeating plus its diameter divided by 2. So the diameter of the radius of the pinion, we already had that. 3 divided by 2 or 1.5 plus 1.5. So that'll be equal to 1.666 repeating inches. And then the radius of the addendum of the gear, that is equal to 0.166 6 repeating plus 4.5. It's just the value that we just got plus another 3. So 4.6 repeating inches. C value that we got, that's 6. That value there is 20 degrees. Our pitch is 6 per inch. So we need to find out what the radius of the base circle is. So we had, we know that the radius of the, well, we know the diameter of the base circle and the diameter of the pitch diameter is related to one another based upon the cosine of the pressure angle. So obviously our radius of the base circle is also equal to the radius, the pitch radius times the cosine of the pressure angle. So if we want to find the radius of the base circle for the pinion, and it's going to be equal to the radius of the pinion times cosine of the phi. That looks more like a theta than a phi to me. There we go. That's better. So that's going to be equal to 1.5 inches times the cosine of 20 degrees. That's right. Cosine 20 degrees. So let's see here. Cosine 20 times 1.5. That gives us 1.41 inches. And then for the radius of the, you know what, we know that the pressure angle doesn't change between the pinion and the gear. The radius of the gear is 3 times the radius of the pitch, 3 times the radius of the pinion, so we can just multiply that value by 3. So the radius of the base circle for the gear is equal to 4.23 inches. So yeah, and we got all the values we need to calculate our CR. So I'm just going to recopy this, put that down here. So that is CR is going to be equal to square root of 1.6666 squared minus 1.666 inches squared minus 1.41 inches squared plus 4.666 inches squared minus 4.23 inches squared, and this is all still on the top, I just ran out of room to write, minus C, so 6 inches times the sine of 20 degrees. All that over 1 divided by 6 per inch, so I'm just going to throw the inch up here, cosine of 20 degrees. So let's see here. 1.666 squared minus 1.41 squared, and then take the square root of that. So this term here is 0.887. 4.666 squared minus 4.23 squared, and then take the square root of that, and that gives us 1.969. Oh, inches. These are both in inches. Minus 6 times the cosine of 20 degrees. 6 cos 20 gives us 5.638 inches. And then on the bottom we have 3.14159 divided by 6 times cosine of 20. Wait a second. I screwed up there. I plugged in cosine instead of sine on this term. 6 times sine 20 degrees. There we go. That's far better. Minus 2.052. Sorry about that. Alright, so on the bottom, 3.1415 divided by 6 times cosine of 20, 0.492 inches. So 0.887 plus 1.969 minus 2.052, that gives us 0.804 inches divided by 0.492 inches. That gives us a contact ratio of 1.63, which is on the high side. We're good. So yeah, there's your calculation of your contact ratio, your determination of whether or not you have interference or not, and we're good to go.